blah, 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 blah. So we've got our scope probes now. Internally, these are both exactly the same. So what these differential probes allow me to do in relative safety, they allow me to make connections to either side of this resistor. It doesn't really matter which way I put these round because there isn't a ground connection, if you like. It really doesn't matter, and I can actually probe any point in this circuit and be relatively safe. I'm not actually going to move these probes around with it live because I stand a good chance of just touching something I shouldn't. I'll just turn it off, but I'll move them round to show you. And again, makes absolutely no difference. So I've just hooked up a couple of the channels on this oscilloscope. So we've got channel 1, and that's actually looking at the full wave rectified voltage across this resistor here, which is feeding the signal into the opto-isolator, which is doing the zero crossing detection. And then we've got the other set of probes connected here, and these are connected to the logic level side. So this is the buffered output from the zero crossing detector, and let's have a look at them on the Powerscope now. Let's just find our 0 volts. Our 0 volts, let's just ground that connection. We'll line that up there, take the ground off. So yeah, there's 0 volts. Let's find, let's do the same for this one. Let's just line it up with something that's about there, isn't it? So hopefully we can see now with the aid of a pointing stick. So when our AC waveform, when it approaches the zero crossing point there, which you can actually see that we actually get our pulsed output slightly before and slightly after the zero crossing point. In fact, I wonder if we can kind of measure that. I suppose we probably could. We would want to reduce our voltage a bit on there. Let's go to 10 volts per division on there. So let's have a look at moving that up to there. So we move it up to there to about that point. So let's see how good our zero crossing detector is. We're on 10 volts per division, so 10, 20, 30. So it's not brilliant, is it? My zero crossing point detector there is actually triggering a little bit before. It's not dead on the zero crossing point, it's actually at 30 volts. So it's 30 volts on either side of that waveform. So we're not crossing dead on zero. So I guess that's not great, is it? I should have done a better job there, so bad me. Well, I've just been having a bit of a rethink about the operation of my zero crossing detector, and I was just trying to figure out what was causing the problem. And I think what I said was that it was being caused by this 220 ohm resistor, this R27, and that what was happening is that as the voltage was actually dropping here towards the zero crossing point, that there wasn't enough current in the circuit to actually keep the opto-isolator switched on. And in many ways I was partially correct, but also I just think that, with a little bit of rethinking, my circuit has actually got quite a problem with it. And I think what the problem is what's actually happening is the current going into the opto-isolator is actually being mainly limited by this R19 at the lower voltages anyway. I mean, obviously this 3.3 volt Zener does actually clamp it, but the actual current is being limited by this 22k here. So it looked as though the problem was starting to occur around the 30 volts point, which is where my detection circuit was saying the crossing point was. And so I think the cause of the problem is that if you put 30 volts across a 22k resistor, you only get about 1 milliamp of drive current, and obviously that drive current is some of that is going to be going through the Zener diode here to reverse bias it, and some of it is going to be going into the opto-isolator to switch it on. But I don't think 1 milliamp is enough probably to fully turn on this opto-isolator. So it's not a simple problem of reducing that resistance value there, that 22 ohms. I think we'd actually have to do something about reducing that. But the problem about reducing that is that it would put up the power dissipation in the Zener, and that is something that I was trying to avoid as well. So yeah, just maybe not a great circuit this. I mean, it's not unsafe or anything, but not a particularly good one. I probably should have thought about it a bit more. But as I did say earlier, this thing was built in about a morning with bits I had lying around in the junk box, and I'm sure with a few more resistors dotted here and there, maybe some trimming here on the on this side of it, we could, before it goes into the Smith trigger, and we probably could have just tweaked it to get slightly better performance, but it was good enough. But really, for the purpose of today, how this circuit operates is a little bit irrelevant. Again, it's more to do with the fact we've got this power scope and what we can do with it. And one thing that I did want to do is I wanted to have a look at the current going through this R27 resistor to find out how much current we were putting through this opto-isolator. Now you can imagine, again, if we were using a conventional scope probe, we would have to clip we'd have to clip the scope probe onto our 0 volts connection on one side, and then we'd have the probe on the other. But if you look at this circuit, there is no common 0 volts here. If we couldn't have clipped it onto there, it would have shorted the resistor out. We couldn't have clipped it onto there, it would have shorted the resistor out. So what we really wanted to do was to take, if we wanted to look at the current going through this resistor here, we'd have to do a differential measurement. Again, this is ideally what this power scope is for, and we can do that. So that resistor R27, I've just put some flying leads on it because the probes on this oscilloscope are a little bit too big. So we're just measuring the voltage here across the resistor, and if we know the voltage across it, that will imply the current flowing through it and the current into the opto-isolator. So let's just have a quick look at that on the scope now. Okay, let's just have a look to see if we can figure out why my circuit's so rubbish. So this waveform here that I'm wiggling up and down at the moment, that's the voltage being dropped across the main, let's call it the main dropper resistor there, and that's dropping at the moment. We're on 50 volts per division, so 1, 2, 3, 4, 5, 6, 7 times 50 is 350. So wow, so we've got 350 volts across there. I suppose I shouldn't be surprised, but I'm more normally working at 3.3 volts or 5 volts, so to see 350 volts in my circuit is always a little hair raising. Right, so 350 volts there, and then this other waveform we've got here that can move up and down, that's the voltage which is being developed across the resistor that's feeding into the opto-isolator. So let's just move them down to about the same point. Let's make that one a bit bigger as well. So when we're at the top of our main cycle, we're going to have effectively 350 volts coming into the circuit. Now this second voltage waveform here can be used to represent the current going into our opto-isolator. So let's just have a look at that. So what is that? That's on, which one am I on? Is that 0.5? Yeah, 0.5. So 0.5, 1 volt, 1.5. I'm going to call it 2 volts just for simplicity. What is that? No, let's call it, it's about 2.8, isn't it? Alright, 2.8 volts. So 2.8 volts, so 2.8 volts divided by the resistance is 220 ohms equals 12 milliamps. Okay. Let's just have a look at it now when the voltage starts to fall. So we're about halfway down on the main cycle there, and we're about 175 volts. So if I just follow this line down here, just to have a look at what voltage we're developing across the opto resistor now, it's going to be different. So let's have a look at it now. 1, 2, 3. It's about 3 times, I think it was 0.5 volts per division. Let's just double check that again. 1, 2, 3. 3 times about 0.5, which is of course 1.5. So let's do our calculation again. 1.5 divided by the load resistance, which was 220. So we're at 6 milliamps now, so our current is starting to reduce. So I'm pretty sure what's happening is once the actual mains voltage starts to fall towards its zero crossing point, and let's call it 30 volts because that's what we were getting. So we plug some numbers in. If we plug 30 volts across that 22k, well, we'll add that one to it because basically that resistor there, 22k, is in series with a 220 ohm. So let's just plug them in. Let's assume we're at 30 volts. So I'm going to put 30 volts in the calculator. If I can switch the calculator on button there. So let's do 30 volts divided by, what did we say? It's going to be 22k plus 220 ohm, but let's call it 22k because, yeah, that's not that significant now. It's 22,000 ohms even. So that gives us 1.36 milliamps. So basically at 30 volts, we've only got 1.63 milliamps of current going into this opto-isolator here. So it's not going to be switched on, it's going to switch off. And that's what's happening. So that's causing the problem. What I would probably need to do there is to actually make it cross closer to zero. We'd actually have to reduce the value of that 22k resistor. So by reducing that value though, we would be dissipating more current across the Zener diode. In fact, I wonder what that would be if we wanted to halve that. So let's say we drop that to 10k. So we'd have about 350 volts, is it V squared over R, 350 times 350 R, which would be 22,000. Sorry, we said 10k, didn't we? Divided by 10k. So if I reduce that to 10k, I'd then be dissipating 12 watts across that resistor. You don't really want to be doing that, so it's probably just not a good way of doing it. Well, I think we've managed to establish there some quite large flaws in my mains detection circuit. So I think the best thing we can do is just move on quickly and never mention it again. So we've got the oscilloscope set up now just to look at the output of a transformer that I have on the bench. And one of the features that this scope does have is a rudimentary cursor. And I do say rudimentary because I think it's fair to say it doesn't work very well, or certainly I don't find it works very well. So I'm hoping you'll be able to see it on your screen. I'm going to zoom the camera in a little bit. I say I'm not sure if you can see it because I can barely see it, but what I've done is I've switched on some cursors here, and hopefully you can see there's a little tiny mark there, roughly where my pointer is. I don't know if you'll be able to see that at all. I can barely see it, it's not very obvious. And what we can actually do is, we've got this number of degrees here, and there's a couple of ways we can increase this the counter and move this cursor along. So at the moment we're at the start of the waveform, but we're at 0 degrees. So what I can also do is, I can, for example, add 120 degrees to where this cursor is pointing, which will take it to there. So what I will do is I'll just do that. I'm going to do 60, 120, 180. I hope you can see the cursor's now moved to there. Now you can actually do the same thing manually because we have this count function here. So at the moment the counter's set to 0 degrees, but if I increase the counter, that's moved the dot along now by 1 degree. So let's move it to 90 degrees, which is going to move it near the top there. Can you see it going up? Nearly there. 80. 90 degrees. Can you see that? Now we'll move it to the 180 position. Which is there, and if we move it to the 360, it's going to be right at the other end of the waveform. So we're at 359 at the moment, and the cursor is just about there. So let's just wind it back, and we'll just wind it back to the 0 point. So watch the count fall, and watch this little cursor move all the way back to the start. Can you see it crawling along? There he is. He's going up the roller coaster. Now he's going to go whee all the way down. Okay, so why would you want to do that? Well, Phase measurement is quite a useful thing to be able to do in mains circuits because you want to look at things like power factor. And I suspect, again, one of the things that this oscilloscope would have been used for, it would be looking for things like three-phase circuits where you want to look at the phase relationship between maybe one phase and another, but you also want to look at the difference between the voltage waveform and maybe current waveforms. So one of the add-on features you could get with this oscilloscope would be to have a current clamp that will allow you to monitor the current going into, for example, your motor or some other piece of equipment. Well, if you know the voltage across the motor and you know the current waveform going into it, you can actually work out something called power factor, and once you have power factor you can do power factor correction, and I'm sure that's one of the things that this oscilloscope would have been used for. But I think it's fair to say that the way they have implemented it is a little bit crude. It could be that there's some way of adjusting this dot and making it a little bit bigger. I have tried, adjusting some of the focus controls and things, and yeah, nothing really seems to help that much. It's a little bit more obvious if I just turn the brightness down there. Can you see that now? Yeah, so that's a little bit more obvious if you turn the brightness down. So we'll just go back up again. And I think that's a little bit more visible now, isn't it? Now, one thing that I have found just massively annoying on this scope is just trying to figure out how to turn on and off some of the channels, because it's really not obvious at all. It seems to be like a combination of these channel select switches on the front panel here, and they kind of pressing switches, and some of them spring out and some of them are kind of permanently in. So let's just see if we can actually get all the channels up. I think we'll just unplug the signal for now. So there's channel 1, so let's put channel 1 at the top. Let's see if we can find channel 2. Well, that's not it. So yeah, that's channel 3. So I think we've got to press this channel 2 button here. So that's appeared up there now. So there's channel 2, 1, 2. So there's channel 3 there. There's channel 3. So we've got 1, 2, 3 channels up at the moment. Can I get channel 4 up? Is it there? Oh, there's channel 4. And it looks like we've got a choice between channel 4 and channel 5. So I'm just trying to move up and down channel 5 now, so I can't move that up. So looks like, is that channel 5? Yeah, it is. So channel 4. So it looks like we can select between channels 1, 2 and 3, or 4 and 5. So actually that's quite obvious really, isn't it? Don't know what I was making a fuss about. Now, as everybody knows, all animals are equal, but some animals are more equal than others. And the same thing can be said of this Powerscope. For example, inputs 1, 2, 3 and 4 are all differential, but input 5 is single-ended. Now the bandwidth also varies. So the bandwidth of channels 1, 2, 3 and 4 is between 5 Hz and 30 MHz to the minus 3 dB point. But for input channel 5, the bandwidth is between 5 Hz and 50 MHz to the minus 3 dB point, assuming that we terminate into a 50 ohm load. Now it's also slightly annoying again that this uses this non-standard socket, because it would be quite handy just to plug in a conventional scope probe here rather than the these enormous things that come with it. But yeah, unfortunately not. And I don't have any form of adapter to actually to plug in a normal scope probe. That's a bit of a shame, because it would be a little bit easier, especially if you want to just use this channel on its own, this single-ended channel, for doing something like monitoring a digital circuit. Now, I don't know if anybody has noticed, but there is one button that's missing from this oscilloscope, which is an alt or chop button. Now, generally, if you're looking at low-speed waveforms, the chop function tends to work better, because if you have alternate selected, you tend to see the scope drawing one waveform, doing one trace, then it draws the other and draws the other, and that doesn't look very good. So for low speed, they tend to use chop operation, but when you actually turn up the time base of the scope, alternative tend to works better. So normally I'd expect to see a button on here which would just let me select either alternative or chop. But one feature that this scope has, the designers have taken that manual control away and it's done automatically. So when the time base is set to below 1 millisecond per division, the chop function is automatically selected. But if we increase above 1 millisecond per division, the scope automatically goes into the alternative mode. Now a lot of the other controls are fairly conventional. We've got our voltage per division select here, and that's the same for all the channels apart from the 5th channel. Now the 5th channel has a different voltage per division range than the other channels 1 to 4, and I think it was probably a little bit of an add-on, because I believe that one of the main uses for this channels is actually more for like an external trigger source. Now because this has only got a much smaller number of volts per division, it just goes from, what does it go from? It goes from 0.2 volts per division to 10 volts per division. This is the channel that I selected earlier when we were looking at our crossover sync pulse that was coming out of the Smith trigger. Whereas traces 1 to 4, which are differential inputs, have a voltage range between 0.1 and a staggering 10. You know, a bulk buy on these press switches, because we've got the option here to ground the input channel or also do the select between the DC or AC input mode, and quite often this is done with a single selector switch on, well, pretty much all oscilloscopes that I've ever used in the past. They combine that into a little lever that you can flick between maybe a DC ground and then an AC, and maybe even a channel off, whereas this one, it's got the 2 functions on 2 separate buttons, and actually that it is a little bit of annoyance that it's caught me out a few times in the last few days. And the other thing that's a little bit of an annoyance is that I haven't found an easy way of actually turning the channels off, because we've got like the push buttons here and I can turn them 2 off, but it seems like you're pretty much always forced to have channel 3 switched on unless you select this. And again, an unusual thing, quite often oscilloscopes have this function to add channel 1 to channel 2, but I actually think it's actually shown as being a multiply function here, 1 times channel 2. So yeah, I'm not exactly sure what all that's about or why you would want to do that, but yeah, it just means that it's not very easy to you know, turn some of these channels on and off. It's just a bit of a fiddle. But yeah, not a big deal, I'm sure. Focus control, intensity, and it does actually go mega bright, this thing. I could illuminate the whole room. You know, if the light bulbs ever go out, I just need to plug this in the corner. Wow, the future's so bright, I've got to wear shades. Okay, I think that's enough of that. Let's turn it around and have a look at its bottom. Now, I think one of the nice features that this oscilloscope has is the ability to output these output signal channels. So basically what it does is whatever signal you apply to the input channel, it provides an attenuated output of it at the back here, and that's very, very useful for plugging in you know, external test equipment. For example, rather than trying to work out what the frequency was on the screen by counting the graticules and looking at the time base, of course it would be much easier to plug in a frequency counter. But you wouldn't want to plug your frequency counter in to directly to you know, like a 3-phase power supply, because it, you know, it's probably 415 volts. You just want to plug in a very attenuated version of that. So this does it for each of the channels separately. So that's very handy. The other thing that it's got this CRT display output. So I'm going to guessing that that's maybe a composite video output, but again, I'm not exactly sure. So on the other side of the panel, we've got the mains input, and the equipment will work between 90 volts and 264 volts AC, and it's telling us that the frequency will work between 48 and 440 hertz, which seems like quite a wide range. In fact, it's a very wide range, and I think the reason they go to that upper extreme of 440 hertz is because a lot of aviation equipment uses high frequency. They don't use 50 Hertz, they use much higher frequencies than that because they want to keep the losses in the transformers down and keep them as light and compact as possible. So if you're working on an aircraft, you're probably working at higher frequencies. And of course it's got the ubiquitous IEC connector for the mains input. Now the other thing that it's got this very substantial, and it is substantial as well, earth screw or earth stud sticking out the back. And it does actually mention this in the instruction manual, and it says if you're not using this input connector, you're not using a properly grounded supply, that it's essential for the for safety to actually ensure that you do earth everything properly using this stud at the back. And again, I'm guessing that if you are working at hundreds or even thousands of volts, it's very important to keep the cover of this equipment. It's a metal box, very important to earth it. But I think for today, that'll do. Thanks for watching. Hope to see you again very soon. Bye for now.